Hello, everybody. Welcome back. In this lesson, we will go over derivative computations. If you recall, up to this level, we have seen the definition of the derivative, and in particular, we talked about the meaning of the derivative. We talked about how the derivative can be applied, or at least like we saw it qualitatively, how the derivative can be applied in geometric or real-world applications. And to begin with, first of all, we recall these facts like the derivative is so important in terms of these applications, and there are many real world applications. But what matters the most in this case is to understand how to compute the derivative. So, what we're trying to do is now, first of all, we know one way of computing the derivative, right? We know the limit definition. But if you think about the limit definition of the derivative that we have already employed in computing derivatives of simple polynomials, it becomes substantially complicated when you work with more functions involving with different components. So for that case, now we need to come up with an easier way of preparing derivative computations. That's exactly the plan in this. So first of all, derivative computations. To get to derivative computations, just with an envision of what we are trying to prepare with more applicability. First of all, the derivative computations are simply nothing other than just like it is a machine, right? In mathematics, when we consider machines, we call them operators. So what we have is like there's an original function, you send that through a black box, and then you come up with something, a different function, and we call that the derivative. And there is a special recipe hidden in this box to prepare f prime or the derivative. And that recipe, we already know it is not a mystery, it is the limit definition. And what happens in this operation, or what happens in this box, is what we call the differential operator, or that particular box is called the differential operator. So whenever you need to take the derivative, this is what you're going to do. You're going to grab a function and you're going to send it through this box. But now, mathematics is not going to work magically like that, right? You need to do the computation, and we need to understand what this box is. So let's do this. So this differential operator, this operator, let's give a name. Let's make our own name for that. Our own name, or the notation, we will call it D, right? So simply you grab a function and you apply D. Now think about this scenario just like an application of a function. If you grab a function and if you just grab a value for x, and if you just input that, and you're going to get a value, right? That value. Now this function is actually acting like a box. It's acting like an operator. It is not an operator in that case. What we call it's a function simply. Now in this case, a function, all right, so when you consider a function acting on functions, there's a precise definition, but we call it an operator. So this is an operator. More precisely, it is the differential operator. So the derivative of function f of x is always computed by sending it through this box of D. Once you grab that function and once you put it inside the argument of this box or this operator D, what you're going to get is the derivative. Now, this is simply a notation, right? And if you have seen calculus content before, now don't forget we have some notations for the derivative already. So what are those notations? We consider the derivative in terms of f prime, or we have d by dx notation, Or we have like sometimes we call it like when you write a function like y equals something, right? You can just compute the derivative. You can write it in terms of y prime when you know exactly what independent variable you're dealing with, or when you need to emphasize the independent variable, you're going to use uh, dy dx notation. So either way, now these notations are already in use in the literature. But now here, by any chance, if you've never seen this notation, don't worry. Now let me show you. This is exactly what I'm going to do. The only thing that I did here is to prepare a new notation, our own notation. The purpose of this own notation is just the same thing as this. Can you see the similarity? D by dx f of x, or you can call it like just when you know the meaning of the independent variable, you're going to call it just d of f of x, the derivative of f of x. The only purpose of that conversation or the only purpose of that new notation is to simplify our writing and to give precise meaning of the action of the derivative. So points to know at this point. Now with that notation on our hand, we will proceed to our toolbox. We will prepare our toolbox. To get to that point, first of all, derivative computations are easy. Now let me tell you, you're going to see like even without knowing limits, even without knowing trigonometry, even without knowing much of algebra, you can do derivatives. So what I'm going to say is derivative computations are easy. How easy? It is very easy. And I'll show you all aspects of it. And on the other hand, uh, this is a skill that you need to have. The ability to compute derivatives precisely is one single aspect that you need to have, is the most important aspect that you need to have out of calculus 1. So if you if algebra, trigonometry, if you have like some difficulties in some other contexts, prepare yourself to contain is this derivative compartment and try to do the computations precisely. If you do that, the rest, anything in calculus 1 can be captured or can be understood well once you start from this particular point. So this is a core skill that you need to earn in calculus 1. How important is it? It is the most important component. You need to know the derivative computations. And then on the other hand, now essential skill does not mean it is uncomfortable. So you can make it comfortable. You can make it just a game. Think about a chess play. When you know how each and every piece is can be moved, right? Whether you play an excellent open game or end game, it doesn't really matter. As far as you know how to play it, you know how to proceed at each step. You know how to move those pieces legally, right? So that's exactly what you need to understand in this scenario. The the most important fact is like when you're comfortable with the basic collection of rules, it becomes just a simple game and it can be enjoyed. Trust me. So without a further ado, let's jump to the derivative computations. Now, right? Again, I'm emphasizing this again and again because this is a key component that you need to earn in this course, and make sure it is your own work when it comes to assignments and exams, and make sure you have good grip on this particular component and you will be confident to bring your calculus 1 to the next course or wherever it is applied. So please pay attention at this point. Important tip at this point. First of all, grab a fresh page. It could be an empty A4 sheet or something, some kind of eye-catching uh, paper, something separate from your ordinary notebook pages. Why do I say that? Because the page that you're going to prepare now, is kind of like a formula sheet. Of course, you're not gonna use this one again and again later, because the purpose of this formula sheet is to identify how simple calculus 1 is. All right, so grab a fresh page, at least the size of A4, right? A regular uh, printer paper, all right? And then title it All I Need for Derivative Computations. So that simply means if I ask you to summarize your entire calculus 1 by the end of this course, you will have a summary now. You start summarizing it at this point. All I need for derivative computation. So in other words, you're going to prepare a formula page for you, right? So prepare it and just hang it on your in your room, right, somewhere, so that you can see it always when you work with the problems. Now, all I need for derivative computations are going to be right here now, right? After titling it now, okay, here, this is my formula sheet. All I need for derivative computations. First of all, I will have two directions here. I will start with formulas, and then I will have rules. It is not really needed like you have two sides of the same page for this. You can write one of the categories in one layer right at the beginning, and then the rules afterwards. It doesn't really matter. But what I'm going to do is to give you everything that you need for calculus 1. All right, the starting step. Now, I will just talk about briefly this what we have here, and your duty is in the meantime to note down this on your uh, note or like let's say uh, the formula sheet. I will call it in that way. All right. So look at this. The formulas. The first one, d of a constant, in other words, the derivative of a constant function. Now, try to visualize a constant function. What do we mean by a constant function? A constant function is a function that does not vary when you vary the independent variable. So it stays the same. It is a horizontal straight line. What is the slope of a horizontal straight line? There is no variance, therefore it is going to be just zero, right? You can use the limit definition to prove this, or just like it is a fact that comes right away. The derivative of a constant is going to be zero. And then the derivative of y equals x, if you consider the line y equals x, what is the slope of y equals x? It is none other than just 1. And then when you consider the derivative of x to the n, x to the power of n, where n is a fixed number, that is a special rule called the power rule. Of course, it is obvious, right? It has the power. It is concerning about the power of a variable. So it is called the power rule. So the power rule is none other than what you see right here. The derivative of x to the n is none other than n times x raised to the power n minus 1. And then when you consider the derivative of the exponential, the natural exponential function, now let me tell you a story at this point. By any chance, if there are any of these transcendental functions, like let's say if you did not have a really good relationship with trigonometry at a certain point, and if you are really like worried about working with trigonometric functions, don't worry at this point, because all you need to know is right here. The derivative of sine is going to be cosine, and you do not need to know about sine or cosine, anything about sine or cosine. It's just about knowing this simple line can help you the computation. The same way, when you consider the derivative of the exponential, now this is the exponential, you should recall it. However, if there's a difficulty behind it, leave it behind at this point and say the derivative of the natural exponential function is that exponential function itself. A quick tip or quick fact. If you consider this function, now this is the most natural function in differentiation story, because it is kind of like an identity. It is like when you differentiate, you end up getting the same function. So that doesn't change. It is an invariant. So that is an amazing property, and you can explore it later. But now, for now, it is just a fact. The derivative of the exponential is ex, write it down. And the derivative of ln of x, ln is none other than the natural log, in other words, the logarithm to the base of the natural exponential, ln e. So, in other words, like log to the base of e. Even if you do not recall that whole background story behind this is what you need to understand here. The derivative of ln of x, whenever you see ln x, and when you have the derivative, when you need to compute the derivative, it is 1 over x. And then, now, do you see? The routine is to have these formulas noted. Now, this is the first batch. And then the second batch is going to be the basic trigonometric functions right here. Note them down. The derivative of sine equals cosine, and be careful to have them uh, written down precisely. Some of them are having negative signs in front. Make sure that you do not drop those negative signs. The derivative of sine is cosine. The derivative of cosine is negative sine x. The derivative of tangent x is secant square. The derivative of cotangent is negative cosecant square. And the derivative of secant square, secant is secant times tangent. The derivative of cosecant is negative cosecant times cotangent. And at this point, you may be overwhelmed because you may feel like, oh, there's a bunch of formulas that we need to memorize. Trust me, memorization is the worst thing that you can do in mathematics at any level. So I will show you the connection between each and every of these formulas in upcoming days. What I need to start with is a summary that you're going to have for your entire calculus semester, entire course of calculus. So that's why, trust me, I'm going to show you how these are built. Most of these formulas, I will prepare most of them. I will show you exactly how those are built. And you can even reduce this entire formula sheet to like 4 or 5 formulas. The rest can be built upon them. But yet, even if you do this, now trust me, how many more formulas to appear? Not many. Until up to calculus 1, the end of calculus 1, this is the worst it can get. Now, the derivative of the inverse sine function. Arcsine means the inverse of the sine function. That is what we have here. And look at this. The connection between that and the derivative of arc cosine. Sine and cosine are non-identical twins in a way. They behave pretty much the same, but with a slight change of phase, right? And can you see the difference between the answers, the derivatives? It differ by just a negative factor. And then the derivative of arctangent, 1 over 1 plus x square. And then the derivative of arctangent arc-cotangent is none other than just the negative of what we got for arctangent. Tangent and cotangent are non-identical twins as well. Same thing goes with secant and cosecant. So when you consider arc-cosecant, you will see the same behavior, right? And note down these derivatives, all of them. And then once you have it, now this is my recommendation. By any chance, if you did not have enough time to note down something like a certain component, in parallel to my explanations. Feel free to come back and just pause the video and note it down, right? And then on the other hand, you can just have it just underneath this one, or you can have it on the second side, the other side of the page. But I recommend to have all of this on one side of the page so that you can just have it on your uh, as a display at any point, right? You can just stick that to the wall or a notepad, right? So you can see it in that way. So when it comes to the rules, the first two rules, now I'm going to use some of these rules. I'm going to show you some of these rules are pretty straightforward. When you need to take the derivative of a summation of two functions, what you're going to do is just to distribute the derivative operator. That's exactly what you tend to do even without, I mean, even if I do not explain as well, right? So what you see here is the derivative of f of x plus derivative of g of x. So that property alongside with the constant multiplication property. In other words, when you have a constant multiplied by a function, you can simply, this constant is not getting involved with the computations, therefore you can pull it out. Just pull it out. Now, can you see the difference between these two scenarios? The derivative of a constant alone, it's going to be 0. But the derivative of a constant multiplied by a function is going to survive based on the strength of that function. Because when you have a constant multiplication here, what's happening is it is nothing other than a rescaling of the given function. So the constant is in fact not just a constant. In this occasion, it is a rescaling factor of the given function. So that rescale remain intact. So you can simply bring it out. That's what you see here, and you're going to differentiate the function itself. So it's that simple. And then, all right, so these two properties together, we call them linearity properties. Linearity. Let me use a better color for that. What would be better? All right. Linearity. Linearity properties. So linearity properties just mean the derivative operative is a linear function. I mean, it's a linear operator. So it acts like a linear function. And it has some extension to uh, upper levels of calculus and mathematics. However, the next step, now, when you have a multiplication of two functions and if you're concerned about taking the derivative, this is called the product rule, and it has a special recipe. The product rule simply says this idea, right? When you need to take the derivative of a product, a multiplication, what you're going to do is to grab the first function first. First doesn't really matter, right? You can switch them. Just grab one function first, take the derivative of it, and this is the original second, right? Original function g, I didn't touch it. I will just multiply by that. Is the original second function, the derivative of the first, original of the second, and then have plus in between, and then switch the order. Original of the first and the derivative of the second. And we will see applications to this. And then, all right, so this is called the product rule. Now, this deserves a separate session, and I will talk about that separately. But right now, in this session, I'm going to show you, you can literally gather all of this information and have one quick review session, and you can say like, oh, now I'm really good with all derivative computations. That's exactly what I'm going to show you, right? So now, the one that you see here is a quotient. Can you see? A function divided by another. So when you have a quotient or when you have a function division of functions, this rule is called the quotient rule. it has some similarity with the product rule. All right. Can you see here in this case, we're going to do pretty much, look at this and this component. It's pretty much the same except for the sign right here. There's a slight difference. And then there is a different component. But let me show you the way it is computed. First of all, in this case, since there's a negative sign in between, order really matters. First, what you're going to do is to grab the top function. Now, if you need to recall this as a formula at a certain point, do not mix it up. When it comes to the quotient rule, always the top first. And our action is taking the derivative. So top first, take the top function, take the derivative. Multiply it by the original second function, and then original first function multiplied by the derivative of the bottom function, and the whole thing is divided by the square, just the innocent square of the bottom function. It has no calculus. Just grab the function and put a square on top of that. If it is just x, you're going to write x square. If it is x plus 1, you're going to write x plus 1 in parentheses and put x square, just square, right? It is that simple. So it is called the chain rule. And then the last, trust me, the last rule that you're going to see in calculus. This is called the chain rule. In the chain rule, what you do is like you work with a function sitting inside another function. Can you see the construct of this function? Now we have function g of x fed into function f of x. Right? When you consider function f with these parentheses, now that is exactly what's going to trap as the inside argument. So that inside argument is none other than g of x. So that is a function in another function. So when you have a function in another function, how do we compute the derivative? This is the simple story. We are going to compute it like by layering, by peeling one layer at a time. We start with the outermost layer. We compute the derivative of the outer function f prime, right? We know the prime notation already, f prime, and then we evaluate whatever that function at g of x, and then we get to the inner layer and we simply just take the derivative, just the plain derivative g prime, and just put them together, bond them, stick them together with a product. And trust me, now this as a summary, this is everything that you need to learn about the derivatives. I know it seemed like little um, dense right here. And let me show you how to answer it. Right? So it may be like, okay, it seems dense, but look at this. Let me just have like just a quick overview. This is my calculus one. Everything on one single page. Yes, I'm just misleading you when I say everything is right here, because this is not everything, right? We are going to do something more, but everything depends on this simple thing. And if you know how to handle this page really well, efficiently, you can do all the other aspects of calculus one. That's a simple uh, observation that we can have. Now, let me show you a couple of things. Now, I'm going to do this. Now, given that you have this formula sheet in front of you, now I'm not going to go back and forth here. So have your formula sheet just besides. Now, when we work with the problems upcoming, I'm going to refer to certain components. I'm going to say like, oh, the derivative of sine x. When I say it, if you do not recall it from your writing, just take a look at it. Then you know what it is, right? And when I say like, I'm going to use the product rule in this occasion, when I say the product rule, you know what that means. You're going to just go ahead and point it out right here on your formula sheet. You know the product rule. And when I take the derivative of ln of x, you should know that's going to be 1 over x. And at a certain point, when I work with an example, if you'd like to work before me, just pause the video accordingly and work with these problems yourself so that you can earn confidence by knowing that you solved the problem even before me. All right. So let's play with a few examples. Now, examples and more examples. Our entire uh, module is going to be based on derivative computations. So we're not going to see any applications at this point. We're going to just play with derivatives. Just compute, compute, compute. Now let me start with this. A simple example, a computation of the derivative. Now look at this. The purpose of this entire fancy new notation, you can have the same notation. Sometimes it could be given in this way, right? D by dx. In most cases, you will be given it in that way. But here I use this fancy notation to give you more precise notion of the derivative. The derivative simply means it's an operator. I operate it on a function and I end up getting an answer. Now, the derivative of this given function. Look at this. I can do this one step at a time. And here, as the first example, I'll show you how it's going to work in each step. But later, I will just do it, I will hand wave a couple of steps. First of all, when you have additions or subtraction, these subtractions are nothing other than the pieces of these constants, and what you have in between is just a plus, right? So when you have plus or minus, it doesn't really matter. This is what you can do. The derivative of 3x to the 7, since it's just addition or subtraction, what you're going to do is to separate them, and then minus the derivative of 5x to the 3 plus the derivative of x square. Let me just, let's do it like this. The derivative of 2x square minus the derivative of 11x and the derivative of 10, a constant alone. What should that be? We all know that is going to be just 0, right? The very first line that we wrote in our list. Now the next step, so I'm not going to have any contribution for this. It just disappears when I take the derivative. And then when I compute the derivative here, I can take these constants out. Do you see the linearity property can be applied multiple times? So 3 times the derivative of x to the 7 minus 5 times the derivative of x cubed plus 2 times the derivative of x square and minus 11 the derivative of x. Now let's do this. 3 times the derivative of x to the 7. This is by the power rule. So 7 x to the 7 minus 1. So that's going to be 6. And minus 5 the derivative of x to the 3, that's going to be 3x square. And then plus 2 times 2x to the 2 minus 1, that's x to the 1, x to the 1 in other words, just x. And then minus 11, and the derivative of x is nothing other than just 1. Now, the next thing that you can do is to combine these constants because those are innocent constants sitting in each step. Why don't you combine? 3 times 7, 3 times 5, 2 times 2, and minus 11. That's our answer. Now, one thing that you can do in the next step is not to do these steps. I just did it for your information to show you the role of linearity properties in the application. My recommendation, don't do it in the next step. You can directly jump all the way up to this step if you want, or all the way down to the answer. So example number 2. Compute the derivative. Now here we have some other functions. No panic, just do the same. Negative 5, I have that constant, right? It is just like a constant. Negative 5 together with now x square. The derivative of x square, I know 2 times x. And minus 3 times, the derivative of sine x is cosine x. I'll write it right away. Minus 7 times ex. Ex is none other than, the derivative of ex is ex itself. So 7 ex plus 2 times ln x. So 2 is a constant, and then ln x is resulting, when you take the derivative, it is 1 over x. Can you see I am not just doing this computation sequentially, I am just writing down the answer right away. And then what is the derivative of e to the 10? We know the derivative of e to the x is e to the x. So what is the derivative of e to the 10? Should that be e to the 10? Now don't forget the most important component here. To compute the rate of change, or to compute the derivative, there should be a variable. If you do not have a variable in it, it is not a function that varies. So what you see right here is none other than just a constant. So when you take the derivative of a constant, what would happen? It will just disappear. Now, if you're not convinced why this is a constant, try to do this. Grab a calculator and try to compute this. Put the exponential to the 10. You will get a value, you will get a number. So it doesn't really matter how that number looks, it is just a number. There is no x in it. So it disappears. Therefore, the final answer, if you simplify this, negative 10x minus 3 cosine x minus 7 ex plus 2 over x, or you can write it like 2 times 1 over x. It doesn't really matter. That's our answer. The next example, again, the same thing. Now I do have different pieces. I'm just trying to recall different pieces. And the different notation, d by dx. It is just the same thing in more standard notation. The, the capital D, or like let's say uppercase D, is our own notation for our computation. Actually, we introduce something ourselves. But now, this is the standard historical notation called a Leibniz notation for differentiation. And it emphasizes which variable you're dealing with. Sometimes when you need to emphasize which variable, now there is an emphasis on that. That is the only advantage. Apart from that, it is just the same thing as capital D. Now take the derivative. This is a constant multiple. So 3 times the derivative of tangent is none other than secant square. It is not a surprise. If you're surprised, go ahead and check the formula sheet. Minus 7 times secant x, which is none other than secant x times tangent x, minus 2 here, minus 2 times x, but the derivative of x is 1, so minus 2, and then the constant will result just 0 when you take the derivative. It's that simple. Single line answers. Don't you see? Like, it's that simple. Example number 4, another different notation. When you have f of x given, now I'm asking you to compute f prime. Look at this. The disadvantage of this prime notation, you cannot ask question in one single line. You need to give the first line with the original function, and then you need to ask for f prime. Compare it with the previous problem. Here I am just giving you the problem even without having any words here. Once you see it, you know it is asking for us to compute the derivative of what's sitting inside the parentheses. Here we are giving the function and then doing all the computations, right? So the starting step. In this case, first of all, to answer this, I can provide the answer in two different ways. So I can give you an idea for two different ways. F of x can be, first of all, simplified. If you do not simplify, can you see you need to have a product? To make it simple enough, if you distribute, you're going to get x to the 2 plus 3 as powers, because powers would add when you multiply, and that is the function you end up getting. And now f prime is just the power rule. Take the derivative of this 5x to the fourth plus 2x. That is the answer. Now, by any chance, if you didn't see this nice distribution, and if you'd like to take it as a product rule. Now, if you take the derivative of this right away, this is none other than the derivative of x square x cubed plus 1. Now, if you try to do it just like that as a product, now don't forget the product rule. It comprises like two pieces. Let me move this a little further and let's buy some space. Now, to do the product rule, this is all you need to do. Grab the first function first, differentiate it. X square has the derivative 2x. Multiply it with the original second function, x cubed plus 1, and then plus. Grab the first function, leave it as it is, and then take the second function and differentiate it. So when you differentiate the second function alone, can you see the derivative of x cubed, that is going to be 3x squared, and then this plus 1 disappears because it's a constant. Now let's try to simplify this. When you simplify the first component, now here you can distribute. So 2x to the fourth plus 2x plus 3x to the fourth. So simplify with the like terms. What you're going to get is 5x to the fourth plus 2x. Look at this. Compare these two answers. With two different ways, we got the same answer. But let me emphasize one important aspect behind this. When you need to take the product of two different functions multiplied with each other, it is not the derivative of each component multiplied with them. So do not mistake it with this. The product is not that simple, like taking the product of the first part, taking the taking the derivative of the second part, and then multiply them together. No, it is not like that. Why? If you take the derivative of the first, it's going to be just 2x. And if you take the derivative of the second component, it is going to be 3x squared. Look at this. If you multiply these two components, you're not going to get this or this. Both are the same, right? You're not going to get that answer. What you're going to get is 6x to the 3. No, that is not the answer. So understand that there is a specific composition behind each rule here, and try to obey exactly that particular rule in the computation. And this, let's consider this as the last example in our computations, not this one. Let's proceed to this. In this occasion, I can do the derivative computations. Now look at this. Here, to take the derivative, I mean, even without doing anything, if I show you the way to write x to the square root of x is nothing other than x to the 1/2 as a power. And then this can be written as a power again, 5x to the -1. And then the next one, x to the 2 in the denominator, that's 7x to the -2. Now, when you have powers, the powers do not have any restrictions, right? You need to use it just as a power. So 3, and then n comes to the front. So 1/2 x to the 1/2 minus 1. 1/2 minus 1 will result -1/2. If you later write it as a positive exponent in the denominator, that would be x to the positive 1/2 in the denominator. But that is none other than the square root of x in the denominator. But I'm not going to do any simplification here. Let me just use the product rule in this, the power rule in that, right? X to the negative 1 minus 1, so it's negative 2. And then the third one, negative 2, comes to the front. So 7, negative 2, x to the negative 2 minus 1, it's negative 3. So just simplify. 3 half here. And of course, if I just, let me just write it down so that you can just see it is none other than x to the positive 1 half in the denominator and then converted to the square root. Even if you do not do this operation and if you leave the answer, in most cases, even in mathematics, it's going to recognize, so don't worry. I'm just trying to show you some meaningful simplifications, but simplification is not what's going to matter. I mean, here, reaching this answer, this is our outcome. If you can reach this step without any issue, you're good. And then computing here, it's plus 5 and x to the negative 2, it's none other than just x squared in the denominator. And right here, uh, positive 14 divided by x to the third, and that's our final answer. And let me give you one more example to play with so that you can see computations in different aspects. Take the derivative, compute the derivative of this function. Now, you can use this, you can do this in two different ways. One is it's a quotient, right? You can use the quotient rule. And try to recognize it by yourself. And we will have further conversation about the quotient rule later. But for now, try to do it just the quotient rule. Or if you think a little, you can convert this problem into something simple. Simplification first. What is the possible simplification? Just having a simple denominator where you can simplify things by separating the denominators is golden in this case. So if you separate x cubed divided by x square, 3x square divided by x square minus 7 divided by x square. So if you keep doing that, now the bottom line is algebra. You learn algebra, try to employ algebra as necessary. Sometimes working with a complicated looking function is not the way, right? You can make it look simplified. You can simplify it by using algebra. That's exactly what I did here. So when I do that, look at this. The first term turns out to be just x. Simplify this, it's just x. The second one, it is 3x squared divided by x squared. That is just 3, which is just a constant. And then the third one, we know how to deal with these kind of problems. It's x to the negative 2 as a power. I will write it as a power now. You know how to answer this. And if you do not see how, go back to the previous problem, previous example. And the whole point, do you see, the derivative computations are just one single side of a paper. You simplified, so you summarized everything in this case. Now, you pretty much summarize the entire semester of entire course of the differential calculus into one single page. And whenever you need to use a derivative computations, whenever you need to do a derivative computation, that's exactly what you need to do. Now, think about this. If you can get that information sitting on that single page into your mind, let's say by working with more problems or just by just looking at that paper itself, that formula sheet itself, if you can inject that content to your muscle memory, you have the entire semester of calculus with you. Isn't that amazing? So to fulfill the best outcomes of this course, all you need to do is to get that one single page into your brain. That's all. Have a brain image of that. All right. So I will help you working with different aspects of these computations. I will work with each and every of these formulas separately. I will work with each and every of these rules separately in upcoming lessons. But if you'd like to see everything, everything is right here. Everything about derivative computations is concluded. All right, so we will have further practice on our next lesson. So with this, we will conclude our current uh, lesson, and make sure to have good practice with the problems that we have on bridges. All right, so that's exactly where we are going to wrap up this lecture, and we will meet on the next one. Enjoy problem solving.